Ammonia is added to an evacuated 6.00 liter flask to a pressure of 8.00 atm and a temperature of 25 degrees Celsius. Carbon dioxide is added to the ammonia to give a total pressure of 18.00 atm. The flask is then heated to 110 degrees Celsius. Calculate the total pressure in the flask at the new temperature when the reaction is complete, assuming 100% yield. So we're given ammonia gas, carbon dioxide gas to create urea, solid, and H2O gas. So here we can see that NH3 was added into the flask. The volume is 6.00 liter. The pressure is at 8.00 atmosphere, and the temperature is at 298.15 Kelvin. Then we added carbon dioxide to our mix. This gave us a total pressure of 18.00 atmosphere. Now, if we take the total pressure, which would be total, at 18.00 atmosphere, and we subtracted by 8.00 atmosphere pressure of ammonia, we'll get the difference, which would be 10.00 atmospheric pressure of carbon dioxide. It also states that we heat the reaction at 383.15 Kelvin, and this is when we get our reaction. So what we want to do is we want to use PV equals nRT, and we want to solve the formula for N, which is in moles, as shown here. So we did just that here. So we can solve for it using PV equals nRT. We can use our initial temperature, atmospheric pressure, and volume, and we get 1.96 moles of NH3 gas. We can do another one using carbon dioxide, and since we found the atmospheric pressure of carbon dioxide, we can now use it for the pressure in our formula. Using the same volume, the same constant R at 0.0821 liter atmosphere mole Kelvin, and also using the initial temperature, because we had the same temperature until we heated up the reaction. So we still use 298.15 Kelvin, and this produced 2.45 moles of carbon dioxide. Down here, we can use a mole ratio to get the moles of H2O. So we use the moles that we were given of ammonia, which is what we found here. We do a mole ratio. We had 2 moles of ammonia with 1 mole of H2O gas, and this produces 0.980 moles of H2O. Then we can do the same thing with the moles of CO2, and we can do another mole ratio where we have 1 mole of CO2, 1 mole of H2O, and this produces 2.45 moles of H2O. Now, based on this, we have our limiting reactant, which would be, in this case, NH3. because NH3 produces the least amount of moles of H2O. With that, we can use the least amount of moles of H2O and do a mole ratio of moles of carbon dioxide. So from here to here, and this produces 0.980 moles of carbon dioxide, and this is the amount that was used in the reaction. With that, we can now input this amount of moles used, but so long as we can subtract the initial amount of moles that we had of carbon dioxide, which I don't have here. So that would be the initial moles, which would be here. So we have 2.45 moles of CO2 and this was the initial amount that we had, and we can subtract that by the amount that was used, and this would give us the amount remaining, which would be 1.47 moles of CO2. Now we can use that to find the pressure of carbon dioxide. We can plug this into our equation of PV equals nRT and solving it in this format. And when we do that, we will also use the new temperature because this is after the reaction. So this would be the new temperature. And we're going to do this for the pressure of carbon dioxide gas and the pressure of H2O gas. That way we can have both pressures. So this would give me 7.71 atmospheric pressure of CO2 gas and 5.14 atmospheric pressure of H2O gas. So now we should have everything we need. We have three gases, H2O gas, carbon dioxide gas, and ammonia. What we're going to do now is we're going to add it all up. Ammonia was used up because that was our limiting reactant, so we have 0 atmospheric pressure left on there. And carbon dioxide, I have 7.71 atmospheric pressure. H2O gas, I have 5.148 atmospheric pressure. When we add all this up together, we'll get the total pressure, which would be 12.9 atmospheric pressure. And this is what they were asking for. The total pressure of the flask at the new temperature when the reaction is complete. And that's how we solve this problem.